Today's going to be 102-1, and we're still in the unit of exponential and logarithmic functions. We're going to solve exponential equations, and so that's our objective. We're going to be solving exponential equations. Now, one thing that we kind of need to remember when we're solving these exponential equations is one of those helpful steps. If you guys remember, if I said that I had a to the x equals a to the y, when my bases are the same, I can assume that the exponents are equal to each other. I could replace the variables with whatever I want, but if the bases are the same, we could set the exponents equal to each other. Now that always applies. That's probably something that we always want to look for, because when we look for that, it's just easier that way. So a few things that we have to kind of examine first is we got to isolate the exponents. So these exponential terms, there's nothing in front here, there's nothing in front here, there's not anything being added, it's quote-unquote isolated. So because it is isolated, it's in that form of a to the x, I want to check to see, can I turn it into this? Because if I can turn it into this to where my bases are the same, then it's going to make my life easier and I get to move on with it. If I can't do that, it's going to be a little bit more complicated, and you're going to see that in our following example. But in this one, I can make the bases the same. This is base 2, and I can make 16 into base 2. And so I get 2 to the 3x. This becomes 2 to the 4th. And so I get 3x equals 4 minus 4x. So now I can add 4x to both sides. So I get 7x equals 4. Divide both sides by 7. I get x equals 4/7. Now there's no domain restrictions. So because there's no domain restrictions here, that's what my value is, x equals 4/7. So you don't necessarily need to check, but always plugging it back in, always a good idea to kind of validate or verify if you got the correct answer. So the first thing I did is I isolated the exponential function. You got to make sure that these pieces are by itself. We're not multiplying or adding anything, not multiplying or adding anything. And the moment that you do that, which is like what we did here, you just continue to solve. So step 2, it kind of branches off. One of them is if you can make the bases the same, solve it that way, which is what I did here. And then part B you're going to see in our next lesson, our next example. So in this instance, I have to isolate the exponent. Well, you see I'm multiplying by this 1,000. So I want to divide both sides by 1,000. And so I get 2 equals 3 to the negative 0.1 t. And to get that t by itself, I can take ln to both sides. So that's where I can't make the bases the same. So because base 2 and base 3, there's no way. So I'll do that next part, take ln to both sides. And I get ln of 2 equals ln of 3 to the negative 0.1 t. Now I can take this and I can move it to the front. And I can use the power rule to be able to do that. And so I get ln of 2 equals negative 0.1 t ln of 3. And so now to get t, since these are all being multiplied by each other now, I can divide both sides by negative 0.1 ln 3. So that cancels out there, that would cancel out there. And so t would equal ln of 2 over negative 0.1 times ln of 3. That's something you'd have to enter into your calculator. So you would go through, you would enter that in your calculator, and that's the value that it would give you. This is the exact value. Entering your calculator would give you the approximate value. This next one, now sometimes if I were, like, for example, I know it says isolate it, but I have this 9, and to get rid of this 9, well, if I divide both sides by 9, I still have a 9, like it didn't disappear. So we have to be a little fancy here, and sometimes being fancy, we can make these bases the same. And so this becomes 3 squared times 3 to the x. Now when the bases are the same and we're multiplying, you add them. So this becomes 3 to the x plus 2. Now once again, we're still faced with that conundrum. I can't make the bases the same. So because I can't make the bases the same, I'm going to go with part B, and we're going to take the natural log to both sides. So then I get ln of 3 to the x plus 2 equals ln of 7 to the 2x. Now that I have this, I can move those values to the front. And so I'm going to get x plus 2 times ln of 3 equals 2x times ln of 7. Now I got to get x by itself. I have x's on both sides. So I can distribute this ln 3 through. So I get x ln 3 plus 2 ln 3. And this is going to equal 2x ln 7. Well, I can't combine ln 3 and ln 7 together because they're different. So instead of being able to just add or subtract x's together, we have to do the other way, which is we're grouping them together. So I want to bring my x to the other side. So I'm going to subtract x ln 3 to both sides. So I get 2 ln 3 equals 2x ln 7 minus x ln 3. Now that there's an x in common, I can factor that out. And so I get 2 ln 3 equals x times 2 ln 7 minus ln 3. And now I can divide both sides by the 2 ln 7 minus ln 3. And so x is going to be 2 ln 3 over 2 ln 7 minus ln 3. Now, if we're going to enter this into our calculator, we just have to be careful. You have to make sure you have parentheses around all that, and you need to have parentheses around the entire denominator since we're adding or subtracting multiple things down there. If you didn't do that, you're going to get some wrong calculations, and we don't necessarily want that. So that's the exact value for that. Example number 4. We have x in the denominator, well, or not x, but our variable t in the denominator. We got to get it out of the denominator, so I can multiply both sides by this 1 plus 3e to the negative 2t. So it cancels out on this side, and I'm going to get 1 plus 3e to the negative 2t times 75, and that's going to equal 100. Distributing the 75 through, I get 75 plus 225e to the negative 2t, and that's going to equal 100. So I'm still in this process here. I'm trying to isolate and get that e by itself, or the exponent. I want to get this by itself. So I can subtract 75 on both sides. So I get 225e to the negative 2t equals 25. Divide both sides by 225. I get e to the negative 2t equals, what is this going to be, 1 over 9. Now I can't make the bases the same. There's no way I can turn that 1 over 9 into an e. I don't know how to do that. So we're going to have to do part B. If you cannot make the bases the same, take the natural log to both sides. So I'm going to take ln to both sides. So I'm going to get negative 2t equals ln of 1 over 9. And then I can divide both sides by negative 2. And so I get t equals negative ln of 1 over 9 over 2. And that right there is the solution. So this one right here, 25 to the x equals 5 to the x plus 6. Well, we have to get into this process of isolating the exponent, but there's multiple terms. I mean, if I subtract the 6 on both sides, I am not isolating either one, so we can't do that. That doesn't help us there. let's see. Well, let's look at it this way. What if I say 25? Can I make that the same base? So we look at 5 to the 2x equals 5 to the x plus 6. Now this looks really familiar. What if I bring all these to one side? Let's see what happens. So I get 5 to the 2x minus 5 to the x minus 6 equals 0. Now this looks like a quadratic type equation. What if I said u equals 5 to the x power? So this now becomes u squared minus u minus 6 equals 0. And so now this will factor into u minus 3, u plus 2, which is 5 to the x minus 3, 5 to the x plus 2, and these equal 0. So I set each one equal to 0. So I can say 5 to the x minus 3 equals 0. Solve for that. Take ln to both sides. I can bring the x to the front, so it becomes x ln 5 equals ln 3. Divide both sides by ln 5, which is just the change of base formula. And so I get x is ln 3 over ln 5. And I do the same thing to the other one. 5 to the x plus 2 equals 0. Minus 2 on both sides. 5 to the x equals negative 2. Take the ln to both sides. I get x times ln of 5 equals ln of negative 2. But oh no, immediately you guys should have caught this. I have a negative inside of a logarithm. I can't have a negative or 0 inside of a logarithm. We said that that is an exclusion to our domain. So immediately you can just stop and say that doesn't work. So this is going to be our only answer. I hope you guys caught that as I was going through that. Next one. Well, it looks like I need to get rid of this 2 out of the denominator, so I'll multiply both sides by 2. So now I have e to the x minus e to the negative x equals 10. Yikes. So let's try and get, well, let's get rid of this negative in the exponent. So I get 1 over e to the x. Man, this is a fun problem here. Now I also have that in the denominator. Now I got to get rid of that, so I can multiply everything by e to the x. And so I'm going to get e to the 2x minus 1 equals 10 e to the x. Now this is starting to look like one of those quadratic type equations, unfortunately. So I get e to the 2x minus 10 e to the x minus 1 equals 0. And so now I'm going to have to use the quadratic formula here. So I'm going to say u equals e to the x. So this becomes u squared minus 10u minus 1. So if I use the quadratic formula, I get negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's going to give me 10 plus or minus the square root. This is 100 plus 4 all over 2. So I'm going to get 10 plus or minus the square root of 104 over 2. I'm not going to bother with reducing 104. That's even though you can reduce into 4, but we're going to punch something into our calculator, so there's kind of like no point with that. But we have to remember this is u equals. Well, we said u is the same as e to the x. So e to the x equals 10 plus the square root of 1 over 4 all over 2. And I have e to the x equals 10 minus the square root of 1 over 4 all over 2. So to get x by itself on both of these, what I'm going to have to do is I'm going to take ln to both sides. And so I get x equals ln of all of this. And then x equals ln of all of this. Now just remember, we might have a negative inside. This looks like the square root of 104 looks like that's bigger than 10, because the square root of 100 is 10. So if that's larger than 10, that means the negative's larger, so this looks like that's not going to work, because I'm going to end up with a negative inside my, it's going to be a negative in here, inside that logarithm. So it doesn't look like that would work. So whatever this would be is the approximate inside the logarithm. That's going to be our answer. Well, these are all fun. One thing that was kind of nice about these problems is as we were going through these problems here, we were seeing like different layers of some of this other stuff that we've been doing in class. So that's pretty cool. All right, so some of the concepts that were discussed today, we solved exponential equations. We did some brief review of when the bases are the same, you set the exponents equal to each other. And we looked at a technique on how to solve them when we can't make the bases the same, and we take ln to both sides to be able to do that. Now, go back through and go ahead and take a look at these different examples. Which examples seemed the most difficult, and why did it seem difficult? Like, what about it seemed kind of weird that was like, oh, like daunting, or there was kind of like that step that seems that you couldn't take that next step forward? And what was a common trait about these problems that is similar to the other solving problems? So were there some things that were similar to other ways that we've solved in the past? I just want to hear from you. And as usual, if you guys have any questions about this lesson, please leave them in the comments.